December 7th, 1941. Fire engulfs Pearl Harbor. The United States is drawn into World War II. In less than 6 weeks, the U.S. military confronts a catastrophe more crippling than any maritime loss, a situation poised to immobilize every tank, truck, plane, and landing vessel in the nation's inventory. Japan has seized control of 97% of the global natural rubber source. Lacking rubber, America's military apparatus cannot roll, cannot take air, cannot wage war. Strategic planners project 18 months before total operational failure. The clock is ticking. What remains unknown is that the answer is already documented, secured in the lab notes of a chemist whose peers ridiculed his tests as pointless, whose procedures were rejected as foolish, whose supplies were viewed as industrial waste. Dr. Waldo Semon dedicated years to heating and blending a fragile, non-functional plastic that all other chemists had written off as a lost cause. His managers instructed him to cease wasting resources. His colleagues mocked his tenacity. Yet in 1926, Semon had inadvertently produced something seemingly unachievable: a pliable, rubbery substance derived from polyvinyl chloride, the most valueless material in industrial chemistry. 15 years onward, that stupid trick would rescue the Allied campaign. This is the narrative of how one chemist's unwillingness to concede defeat, matched with U.S. industrial might performing at near superhuman levels, turned a ridiculed experiment into the synthetic rubber initiative that allowed millions of soldiers to advance, battle, and triumph. It is a tale of chemistry, dire straits, and the instant a scorned innovation turned into the deciding factor between winning and losing. January 1942, Washington. The War Production Board calls an urgent session. The data is disastrous. The U.S. Armed Forces need 600,000 tons of rubber each year. Civilian use requires an additional 600,000 tons. The nation's strategic rubber stockpile holds precisely 70,000 tons, just 6 weeks' worth at wartime usage levels. Japan dominates the Dutch East Indies, Malaya, and French Indochina, where 97% of natural rubber originates. The British control Ceylon, yielding the last 3%, hardly sufficient for their own requirements. All military transport depends on rubber. One tank consumes half a ton. A warship demands 75 tons. A bomber needs half a ton, merely for tires, hoses, and seals. The typical Army truck holds 300 separate rubber parts. Lacking rubber, planes are grounded. Landing gear tires, hydraulic seals, fuel hoses, and electrical insulation all demand rubber. Vessels cannot function. Innumerable gaskets, seals, and vibration absorbers require rubber. Troops cannot advance. Footwear needs rubber soles. Cannons cannot discharge. Recoil systems rely on rubber buffers. The head of the Rubber Reserve Company provides the analysis that hushes the attendees. Gentlemen, we possess precisely enough rubber to maintain military functions until April. Beyond that, we confront total strategic gridlock. We are unable to win this war lacking rubber. We cannot even wage this war lacking rubber. The answer appears clear. Manufacture synthetic rubber. Yet in 1942, synthetic rubber is a lab experiment, not a large-scale fact. Standard Oil and IG Farben created a method with butadiene and styrene to make Buna S rubber, yet U.S. output in 1941 was only 8,000 tons. The armed forces require 600,000 tons per year. Increasing output 75 times over in months seems unfeasible. President Roosevelt signs Executive Order 9025, establishing the Rubber Supply Agency with unrestricted power and financing. The objective is mad. Construct from scratch a synthetic rubber sector bigger than the nation's whole pre-war rubber usage, functional inside 18 months. Wall Street experts label it a delusion. Chemical engineers deem it impossible. Roosevelt's reply becomes historic. The experts claimed it was unachievable. Find me individuals who aren't aware of that. What the specialists were unaware of was that the basis for synthetic rubber was already present, hidden in studies everyone had rejected. And that basis was laid by a chemist in Ohio, who endured 15 years of mockery for attempting to make trash pliable. Waldo Semon was born in 1898 in Demopolis, Alabama, raised in hardship that made university seem attainable. But Semon had a quality surpassing poverty, a compulsive inquisitiveness regarding why substances acted the way they did. He earned a scholarship to the University of Washington, received his bachelor's in chemistry, and finished his doctorate in 1923, researching physical chemistry with the esteemed Professor Francis Rutten. B.F. Goodrich employed Semon right away, placing him in their research lab in Akron, Ohio. His first tasks included enhancing rubber adhesives and creating new coating substances. The job was standard, expected, and dull. Semon desired to make something completely novel. In 1925, Goodrich tasked Semon with finding an application for polyvinyl chloride, or PVC. This polymer was found in 1872 by German chemist Eugen Baumann, who had inadvertently made it by exposing vinyl chloride to daylight. The substance that formed was stiff, fragile, and seemingly valueless. For 5 decades, PVC stayed a chemical oddity, intriguing conceptually, unusable practically. Each chemist who studied PVC arrived at the identical finding. The substance was too stiff for real-world uses. Its fragility prevented it from being shaped usefully. It could not be molded, extruded, or manufactured. The field of industrial chemistry had advanced, chasing more favorable polymers. Semon, however, viewed PVC from another angle. If the substance was overly stiff, maybe chemistry could render it pliable. The accepted knowledge indicated this was unachievable. PVC's molecular framework secured its chains in stiff arrangements. Applying heat to PVC merely broke it down. Introducing solvents would either dissolve it or do nothing. Semon proceeded regardless. He initiated a set of tests that his peers publicly ridiculed. He blended PVC with different substances, plasticizers, oils, resins, and exposed the blends to heat and pressure. The other chemists deemed it foolish. "You cannot make PVC pliable," they informed him. "You are squandering time on trash chemistry." For a year and a half, Semon met constant failure. PVC blended with mineral oils stayed fragile. PVC blended with vegetable oils broke down into ooze. PVC blended with different solvents either dissolved or remained stiff. His manager proposed shifting to more hopeful projects. Semon asked for another 6 months. Then, one morning in 1926, Semon attempted a new approach. He blended PVC with tricrylyl phosphate, a substance typically utilized as a gasoline supplement, and exposed the blend to extended heating at precisely managed temperatures. Upon opening the reaction container, he discovered something that ought not to exist: a pliable, rubbery substance that could be bent, twisted, and elongated without tearing. Semon had stumbled upon plasticization, the method of introducing tiny molecules between polymer chains, enabling them to move past one another. The stiff PVC framework stayed complete, yet the plasticizer molecules functioned like microscopic ball bearings, permitting pliability while preserving strength. His peers were not impressed. "It isn't actual rubber," they noted, accurately. "It is only flexible plastic. What is its purpose?" Semon lacked a solid response. Pliable PVC was not exactly rubber. It was unable to stretch to the same extent, unable to rebound from distortion as fully. It appeared to occupy an uncomfortable median space between rubber and plastic, not really fit for either use. Goodrich registered patents on Semon's finding, but opted against commercialization. The firm was focused on rubber, and pliable PVC was not rubber. Semon pressed on with his research, refining the plasticization method, testing various plasticizers, and documenting the substance's qualities. Yet flexible PVC stayed a lab oddity, intriguing but non-functional. By 1940, Semon had dedicated 14 years to a substance no one desired. His professional life stagnated. Junior chemists overtook him for advancements. His manager proposed a move into administration. Semon continued testing PVC. Then Japan seized Singapore on February 15, 1942. The rubber shortage shifted from hypothetical to urgent. The U.S. required synthetic rubber, required it in amounts calculated in the hundreds of thousands of tons, required it in mere months. The Rubber Reserve Company called urgent sessions with all chemical firms that could handle massive output. Standard Oil showed its Buna-S method, originating from German tech. DuPont proposed neoprene, a synthetic material they created in the 1930s. Goodrich dispatched Dr. Waldo Semon, whose talk on flexible PVC was greeted with doubt. "Your substance is not rubber," procurement officials observed. "It lacks rubber's elasticity. It cannot substitute for natural rubber in tires or the majority of uses." Semon concurred. Flexible PVC is not a rubber replacement for most functions, but it can supersede rubber in numerous functions where pliability is more important than elasticity. Electrical insulation, hoses, gaskets, boots, ponchos, and hundreds of other Army supplies now using up rare natural rubber. The procurement officials examined Semon's examples. Pliable tubes, sheets, and formed items that appeared like rubber, felt like rubber, yet were not rubber. "Can you manufacture this on an industrial level?" they inquired. "We have not yet tried," Semon conceded. "We possess laboratory methods that function perfectly on a small level. Expanding to industrial output will mean overcoming many engineering hurdles." How much time would expansion need? Semon computed in his head. Standard development would need 3 years at least. Pilot facility, process refinement, engineering design, building, trials. But this is not a standard situation. Can you accomplish it quicker? Grant me the power, money, and release from typical supervision, and we shall see. The agreement reached Goodrich on March 20th, 1942. Semon obtained unrestricted funds, top national priority for supplies and machinery, and the power to requisition any needed resources. His objective: establish industrial-level manufacturing of flexible PVC inside of 6 months. The other option was millions of troops lacking boots, planes lacking hoses, and transports lacking seals. Semon gathered a group of chemical engineers and initiated the most concentrated development effort in the history of plastics. The difficulties were enormous. Lab methods that functioned flawlessly with 1-pound amounts failed disastrously with 1,000-pound amounts. Temperature regulation turned into a nightmare. PVC broke down if overheated, remained stiff if underheated. Blending 1,000-pound batches needed machinery that was not available. Semon overcame issues via persistent experimentation. When standard mixers failed to manage PVC's thickness, he engineered specialized mixing gear, built in Goodrich's own shops in just weeks. When temperature regulation was unachievable in big containers, he created continuous flow processing, having material move through temperature-managed areas. When plasticizer dispersal led to uneven products, he devised new blending techniques utilizing shear forces. By September 1942, Goodrich had functional pilot facilities manufacturing flexible PVC at speeds surpassing 1 ton daily. Army inspectors evaluated the substance comprehensively: temperature endurance, chemical resilience, pliability, toughness. Flexible PVC cleared all tests for uses that didn't demand genuine rubber elasticity. The War Production Board mandated instant, full-level manufacturing. By December 1942, 3 Goodrich facilities were making flexible PVC 24/7. By March 1943, output surpassed 10,000 tons each month. By June, 20,000 tons. The substance poured into Army supply lines: electrical insulation for planes, fuel hoses for transports, ponchos for troops, gaskets for machinery, and boots for foot soldiers. Yet flexible PVC was just a single part of the synthetic rubber answer. Genuine rubber substitution demanded Buna-S, and that initiative confronted even greater obstacles. The Buna-S synthesis needed butadiene, sourced from petroleum, and styrene from ethyl benzene. In 1941, the U.S. made almost none of either substance at the necessary volumes. The rubber initiative grew into the biggest industrial mobilization ever. The government funded the building of 51 synthetic rubber facilities, 15 butadiene facilities, and 29 styrene facilities. The complete investment surpassed $700 million, comparable to over $12 billion now. Building schedules that typically demanded 3 years were shortened to 8 months. Facilities planned on Monday were being built by Friday, and manufacturing rubber by the next spring. Standard Oil's Buna-S method formed the core of U.S. synthetic rubber output. The chemistry was direct. Butadiene and styrene blended in a 3-to-1 proportion, polymerized with free radical initiators at managed temperatures. But expanding to industrial output meant solving thousands of engineering problems. Butadiene manufacturing demanded cracking petroleum at exactingly controlled temperatures. If too cool, the output fell. If too hot, the butadiene broke down. The catalysts needed rare metals, chromium, aluminum oxide, procurable only in scarce amounts. Refinement required fractional distillation towers running at highly precise temperatures. Styrene manufacturing began with ethyl benzene, made by combining ethylene with benzene. The ethyl benzene was next dehydrogenated, hydrogen atoms removed, yielding styrene. This method needed temperatures over 1,000 degrees Fahrenheit, specific catalysts, and exceptionally pure source materials. The polymerization process itself required compulsive regulation. Temperature shifts of 5 degrees spoiled whole batches. Contamination from oxygen halted polymerization. Too much initiator produced low-grade rubber. Not enough initiator left unused monomers. U.S. chemical engineers fixed every issue using sheer trial and error. When catalyst stores dwindled, they created substitute catalysts. When temperature regulation faltered, they engineered superior control systems. When contaminants led to failures, they constructed cleaner plants. When they required fivefold the chemical engineers available in the U.S., they instructed petroleum engineers, mechanical engineers, and even sharp high school graduates in rapid courses lasting weeks. By late 1943, U.S. synthetic rubber output topped 100,000 tons per month. By spring 1944, output eclipsed natural rubber usage from prior to the war. The unachievable had become standard practice. The rubber initiative triumphed due to U.S. industrial might, performing at levels that appeared extraordinary. Factories materialized in months where none had been. Chemical facilities making rare substances at unprecedented volumes started functioning within a year of groundbreaking. Skilled laborers emerged from urgent training courses that condensed years of schooling into weeks of focused teaching. Dr. Waldo Semon's flexible PVC emerged as a vital element of this triumph. While genuine synthetic rubber substituted for natural rubber in tires and elastic uses, pliable PVC substituted for rubber in thousands of Army items where pliability was more important than elasticity. Electrical insulation, hoses, gaskets, ponchos, tents, boots, gloves, medical gear, and communication line insulation. The inventory spanned hundreds of types. By the war's conclusion, U.S. manufacturing of flexible PVC surpassed 200,000 tons per year. The substance Semon and his peers had ridiculed as valueless trash had turned into a crucial part of military logistics. The stupid trick of blending and heating PVC had established a completely new category of materials that still prevails in contemporary life. Vinyl floors, plastic pipes, insulated wires, and endless consumer goods find their roots in Semon's unwillingness to concede that stiff polymers had to remain stiff. The wider synthetic rubber initiative manufactured over 820,000 tons in 1945, exceeding the U.S. total pre-war rubber usage. The initiative engaged over 70,000 laborers, used massive amounts of petroleum and chemicals, and signified an industrial mobilization so huge it appeared unfeasible until it was done. Following the war, Semon obtained the American Chemical Society's top awards for his PVC plasticization efforts, but true to form, he stayed centered on research over accolades. He possessed over 115 patents in varied areas: rubber chemistry, plastics, adhesives, and coatings. He kept working at Goodrich until he retired in 1963, still testing new substances, still chasing concepts others rejected. In a 1970 interview, Semon mused on his career. "People inquire why I continued working on PVC when all said it was valueless. The reply is straightforward. I trusted the substance had a potential that others failed to notice. At times in science, the most significant findings arise from rejecting accepted knowledge. My peers believed I was foolish for heating and blending trash plastic. Perhaps I was foolish, but foolish tenacity made something helpful." The journalist pushed again. "Did you grasp PVC would grow so significant?" Semon smiled. "In 1926, I believed I had made an intriguing lab oddity. In 1942, I understood it could save lives. By 1945, it was evident that flexible PVC would revolutionize modern production. Yet even at that point, I could not have foreseen how completely vinyl substances would control modern existence. Occasionally, you make something whose total impact only appears decades afterward. Presently, worldwide PVC output surpasses 40 million tons a year. The substance is found in pipes, medical gear, building supplies, car components, and thousands of consumer items. Every vinyl record, every plastic credit card, every insulated electrical line follows its ancestry to Semon's stupid trick of blending plasticizers with valueless stiff polymer and adding heat. The synthetic rubber initiative remains a testament to U.S. industrial might, activated in a crisis. In 3 years, the U.S. built from scratch a chemical sector bigger than its pre-war rubber usage, created new substances and methods, instructed tens of thousands of laborers, constructed dozens of huge plants, and manufactured rubber at levels that met not only U.S. needs but Allied demands. The initiative cost $700 million, yet it rescued the war campaign. Lacking synthetic rubber, an Allied win would have been unachievable. Tanks would have remained stationary, missing treads. Planes would have been kept down, missing tires. Vessels would have been immobilized, missing seals. Troops would have marched in substandard footwear. The whole Allied military apparatus relied on rubber, and synthetic rubber sustained its motion. Dr. Waldo Semon passed away in 1999 at 100 years old, having seen his lab oddity change into a vital element of modern society. His death notices mentioned his technical accomplishments, his patents, his awards. But maybe his most vital contribution was showing that tenacity counts, that rejected concepts sometimes hold concealed worth, and that stupid tricks sometimes alter the globe. Ultimately, millions of U.S. soldiers triumphed in their fights because one chemist declined to abandon a concept everyone ridiculed. They moved through Europe in boots with synthetic soles, traveled in transports with synthetic seals, and hoses, operated gear insulated with flexible vinyl, and were provisioned by a supply system functioning on synthetic rubber. They triumphed because Waldo Semon was excessively stubborn to concede that stiff plastic had to remain stiff, too tenacious to discard valueless substances, and too centered on potential to mind the ridicule. The stupid trick of heating and blending trash plastic had rescued the Allied campaign. At times, the most significant innovations originate from individuals unaware their concepts are deemed unachievable. At times, tenacity counts more than genius, and at times the substance everyone rejects as valueless emerges as the basis for victory.